How's it going, everyone? So we're finally going to finalize this chapter by looking at a learning module that's focused on reducing distributed loads. So what is a distributed load? Well, in the majority of our daily lives, when we think about bodies that are subjected to forces, it's very common for that force to actually be a pressure. And that occurs anytime that we have a body that's subjected to a fluid. A fluid, of course, would include the air around us, something like a wind here. If we have a sign that's outside and we have a wind blowing against it, we're not necessarily going to describe the loading of the wind on that sign by a single force value. We're going to describe it by a force density or a pressure. And at 150 pascals, of course, pascals is the SI unit of pressure. We're not describing, in order to get the force over a little bit of particular area, I would need to take that area and I would need to basically add up all of the density over that area using the techniques of calculus, which we'll talk about in a minute. But since this is so common, where we're designing support structures for bodies that are subjected to distributed forces, wouldn't it be nice if, although the force itself in real life is distributed, if we had the ability to describe it by an equivalent force coupled system, just like we did in the prior chapter, and we do. So to make the math easy, the book kind of focuses on one-dimensional examples of distributed forces in this case. So if we focus over here, first and foremost, it's important to realize what W of x gives you. So if I take this function W of x, which in terms of this curve just describes the height at every point of x, it's not giving me the force at that point. It's giving me the density of that force. And kind of the same idea that I was saying for the sign that was subjected to the wind. If you want to determine how much force is acting around some local point on that beam, you have to take a little chunk of the beam, right? Because the value of that density function at any point isn't equivalent to force. Your book doesn't do a good job explaining that. Very few books do. But if you take a very little narrow slice, right, and you take the area under that density curve, you can determine what the force is acting on that little slice. And that similar idea that always happens in a calculus-based approach. Well, if you think about the equivalent force acting over the whole beam, well, what if I just added those little density slices up? Well, that's going to work great. But the problem is when you have a little slice of the density, it's easy to get the width. That's whatever infinitesimally small value you have, your delta x. However, the height of that for a general function in curvature is not going to necessarily be a rectangle because that function could vary over the domain of the rectangle. However, if you make that rectangle small enough, you can eventually approximate the height on both sides as being equivalent. And then if you took all of those little areas and you added them all up for every value of x, you would be able to determine the resultant force acting upon this object. So this is just the principle if you've taken an integral calculus course of the Riemann sum actually converging to the integral when the width of your individual infinitesimal area elements goes to zero. So that's all this is saying here. I mean, they're making it very hard, but if you have a function, a density function of force acting on a beam, if you can just determine the area under the curve in any way you can, that area is equivalent to the equivalent resultant force by definition, because this is a force density. So if you integrate it, it will have units of force. Now, do you have to integrate? Well, maybe. Well, what if it's just a simple geometrical type distribution? What if it's uniform? Well, if this density were uniform over the beam, I can take an integral, but I know that the definition of the definite integral over that domain is just the area under the curve. So if it were uniform, I take length times width. If it were rectangular, I could do it as well. So a lot of your problems in the book won't actually ask you to make that integral using the techniques of the antiderivative that you may have learned in calculus. And I think when I try to determine the test problem for this section, I'm more interested in choosing a type of shape where the integral could actually be computed without calculus, not because calculus isn't important as engineers, it definitely is, but it kind of teases or decouples me being able to see, oh, this person doesn't know how to integrate versus they don't understand the underlying concept. So key point, if you have a distributed force over the beam, find the area under the curve, that's generally done through integration, but do it however the easiest way to do it is, and that is the magnitude of the resultant force. So that's to say, in terms of the tendency of that force distribution to translate this beam down, you could put that entire distribution over it, or you could just put a single force over it. Now the next question is, where should you position the force to have the same rotational effect? So what this is showing you here is if you have any of those little infinitesimal force slices, naturally they're going to tend to rotate that beam about the origin in the clockwise direction. That's what this is saying here. A little infinitesimal force chunk will rotate the beam in the clockwise direction about the origin. How would I determine what that is? Well, it's the same way that we do any moment. I need the perpendicular distance, which is just going to be however far I am away from the origin. That's my variable x, times the magnitude of the force. And the magnitude of the force is what we're calling this dF. Remember, it's like a delta F. And force is the area under the density curve. So that's all they're saying there, is that the differential amount of force associated with a little rectangle is just the area of that little rectangle. So what I have here, if I ignore the integral sign, is just the tendency of one little rectangle to rotate in the clockwise direction. What I'm doing by integrating over the span of the beam is adding up all those individual rotations. So if you think about it, if this density were uniform, the chunks of the density farther away from the origin are going to tend to rotate more strongly than the chunks that are near the origin because they have that bigger lever arm, right? So that's all that's going on here. We're just integrating because we need to continuously sum the tendency of each little infinitesimal area element under the curve to rotate in the clockwise direction. So what's going on next? So that's how I would determine the tendency of the distributed load to rotate in the clockwise direction. I know I can describe that distributed load by a single equivalent force. The problem is I just don't know where to apply it to have the same effect. So what they're showing here, this x bar times FR, is can I find this location, which I'm denoting as x bar, such that that equivalent force would produce the same rotation about the origin as that entire distribution. And you probably know that that reason they're using x bar is that's actually called the centroid of this distribution, right? It's kind of when we get eventually to the idea of centers of mass, if that distribution were uniform, what would I find? If I put my finger halfway out along the x-axis and also halfway up along the y-axis, it's kind of the balancing point of that area. But that's just the x location of the centroid of the curve. But that's a mathematical thing. In terms of a physical intuition thing, it's how far out I'd have to put a single force to induce the same rotation as that distributed force. So what the book is showing you here is you can use that to solve for what that x location is. Because you know this, you get it just by integrating the entire curve. And in general, you can compute this integral for most functions that are relatively well behaved. Of course, you might have to get into using integration by parts depending on the nature of the function here. That's why we won't do any crazy mathematical examples. So example 1, until you learn more about centroids, we'll determine only rectangular and triangular distributions. Again, the reason that they're doing that is it's easy to determine what the area under the curve is. So let's look at the rectangular example first. What would be the resultant force? Well, if there's 400 pounds of foot, that's the force density across that beam, and it's 10 feet long. It's just 4,000 pounds, right? If I take the area under that curve, it would be the height, which is the value of that density function, 400 pounds per foot, times the width, which is 10 feet. So that's how they're getting that 4,000 amount. Here, if it's a triangle, you just need the height of the triangle, which is 600 newtons per meter, times the base, and you take half of that, right? So that would be, let me see if I can do the math, 1,800 newtons, right? I'll take the half of 6, which would be 3, times 600 would be 1,800 newtons. That's the resultant force. And how far back do you have to put it away? Well, they're just saying for now, until we actually do the integration, you can just rely on the textbook in order to determine that part out. So in terms of, let me show you, actually, you kind of, we already talked about all of this. So like I said, this is really just a foreshadowing for calculations that are going to come. I think it's in chapter 6 of the book. So we'll probably start to look at that in a little bit of detail next week. But if it's been a while since you've done integrations, you will want to refresh on those because we will need to do them in order to determine centroids, or alternatively, you can just call them moments of areas. So sorry chapter 4 was so long. We really had a lot here, but I hope you were able to pick up the content this week.